Illustration of Bellman Ford algorithm. In the last lecture, we learned about Bellman Ford algorithm. We learned what are the steps to be followed. That is, we have to relax each of the edge v minus 1 times in order to find single source shortest path using Bellman Ford algorithm. What is single source shortest path? That means from a source vertex, you will find shortest path to all other vertices in the graph. Whatever vertices be there, to all those vertices, you will find shortest path from this single source vertex. This is what Bellman-Ford algorithm is for. What we are going to do in this lecture is, we'll take a graph and on that graph, we'll see how each of the iteration is working and how can you find shortest path to all the vertices in that graph using Bellman-Ford algorithm. Let us start by taking a graph. Let us say our graph is something like this. You have a source vertex A. From A you can go to B. This is B. Here let us say you have vertex B. From B let us say you can go to another vertex, or maybe C is here. This is your vertex C. From A you have a path to C. Then from B and C, let us say you have a path to another vertex D. From C you can go to D. From B also you can go to D. Then we'll have one more vertex E here. C has a path to E. And then one more vertex F. To this F, let us say you can reach from both E and D. Then this will be EF. Let us keep DF as well. Okay, this is our graph. Or let us keep one more edge. Let from D to E there be an edge. Okay, this is your graph. Next thing is, you have to put weights for each of these edges. AB, let this be 1. Let AC be 2. This be 4. We'll have a negative weight edge as well. Let this be minus 2. Why am I putting negative weight here? Because if there are negative weight edges are not present, then you can anyway use Dijkstra's algorithm. The whole purpose of Bellman-Ford algorithm is in order to handle negative weight edges. That is why I put a negative weight edge here. Then CE, let this be 4. This is 1, 1, and let this be 3. Okay. Now I have weights for all the edges that I'm having. Let us see how can we find shortest path from a source vertex A to all other vertices using Bellman-Ford algorithm. For Bellman-Ford algorithm, what should we do? What did we discuss in the last lecture? First, you will have a distance matrix. So in the last lecture, we didn't actually discuss about matrix because we didn't go to implementation part. That we'll see in the lecture. We will discuss the algorithm for this. That is, we'll write code for this. There we'll discuss those things. Here I'm just using a distance matrix. Okay. So this is my distance matrix. What will this have? This will have shortest path to all the vertices as of now. So in the beginning, what did we discuss in the last lecture? What should you have? Distance to source vertex should be 0. So distance to A is 0. What about distance to all other vertices? We discussed in the last lecture that distance to all other vertices should be kept as infinity. So B, C, D, E, F, distance to all these will be kept as infinity for now. This is infinity, this is also infinity, 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 infinity. When I write infinity, practically it just means a very large number. Okay, we are going to find the shorter paths. So in order to find the shortest path, in each step we'll be finding shorter paths, and finally we'll reach the shortest path. Okay, I'm going to do the first set of relaxation. This is what I want you to understand. How exactly is relaxation working? How can you relax all the edges? This is what I want you to understand. What I'll have is, I'll have my new distance array here. Okay, we'll have A, B, C, D, E, F. This is my new distance array. Okay, I'm going to look at my old array and I'll make updations in my new array. This is my old state, that is starting state. I'm going to do first relaxation. After first relaxation, I'll have this new array. Okay. What am I going to do in relaxation? I'll pick each of the edges and I'll relax them. Let me pick edge AB first. If I relax AB, what happens? Previously, distance to A is 0. So, distance to A plus weight of edge AB, that will be 0 plus 1. Is this lesser than the existing distance to B? Yes, it is lesser than the existing distance to B. What did we learn in the last lecture? In the last lecture, we learned whenever you are relaxing any edge UV, which is having a weight W, if it happens that distance to U plus the weight W, if this is lesser than distance to V, what should you do? This is W. If distance to U plus W is less than distance to V, then what should you do? You should update distance to V as distance to U plus W. Here you have a case. You have a case where distance to B is presently infinity, which is very large. Distance to A plus weight of edge AB is 0 plus 1, which is 1. What should you do then? You should update distance to B as 1. So distance to A will anyway remain as 0. That is the source vertex. Distance to B is updated as 1. Why am I not updating here? That is because when I am updating all other vertices here, I'll take this as reference. I should not take this as reference. I should take the old ones as reference, and then I should be constructing the new distance matrix. That is why I'm looking into the previous state and I'm updating present state. Okay. Edge AB is relaxed. Next, let us say I'll pick edge AC. AC is of length 2. AC is from A to C. Distance to A is 0 plus, that is here distance to A is 0 plus edge AC is 2. This would mean the new distance to edge vertex C is 0 plus 2, which is 2. This is lesser than existing distance, which is infinity. So I'll update distance to C as 2. Next edge, let us say I'll pick this particular edge, CE. If I take CE, what happens? Distance to C is anyway infinity. So if I add 4 to infinity, it will be infinity only. So there is no updation possible. So distance to E, that will remain as infinity. That will remain as infinity. Next, I am taking edge BD. This is also the same case. Distance to B itself is infinity. So adding 4 will keep it as infinity. So distance to D is infinity. Next, I'll take edge CD, this one. If I take CD, CD is having a weight minus 2. But the problem is distance to starting vertex C is already infinity. Infinity plus minus 2 is again infinity. So distance to D will remain as infinity. I have already updated infinity. It will remain as infinity after relaxation of edge CD. If you relax DF and EF, again the case will be same. Same with DE as well. All of these are having existing distance to the starting vertex as infinity, which means even if you relax the edge, those will remain as infinity only. So this will be infinity. What will you do now? You know this is your new distance matrix. So I'll update the values here to the values of, so one set of relaxation is done. Okay. One set of relaxation is done. Now I'll put here 0, 1. I'm copying this. Okay. I'm copying from this particular matrix. Infinity, infinity, infinity. This is my present state. So as of now, number of relaxations done is 1. Totally, how many relaxations I can do? V minus 1 relaxations. How many vertices do I have? 1, 2, 3, 4, 5 and 6. I have total of 6 vertices, which means at max I will do 5 relaxations. Okay. As of now, 1 relaxation is done. Let us move on to the second relaxation. When I do second relaxation, what happens? When I'm doing second relaxation, I will take this as my reference. I'm going to relax all the edges again. To distance to A is 0 only. I'm going to relax AB. What happens when I'm relaxing AB? Distance to A is 0 plus distance to B is 1. So AB will remain as 1. Distance to A, I'm next relaxing AC. Distance to A is 0 plus 2 will remain 2. So distance to C is 2. Now we are going to see some changes here. If I relax BD, what happens? If I am relaxing BD, distance to B that is already existing is 1. To that 1, I am going to add 1 plus distance BD. BD is 4. That would mean my new distance is 5. Existing distance to D is infinity. Existing distance to D is infinity. 5 is better than infinity, so I'll put 5 here. Next relaxation I am going to do on edge CE, let us say. If I am doing on CE, distance to C, as of here, distance to C is 2. So 2 plus CE is 4. 2 plus 4 is equal to 6, which is better than the existing distance to E, which is infinity. So I'll update E with 6. I have relaxed CE now. Next is CD. If I relax CD, what happens? Distance to C is 2. To this distance to C, I will add 2 plus minus 2. This is having value minus 2. 2 plus minus 2 will give me 0, which means my new distance to D can be 0. Presently it is 5, but I have an option to update it to 0. What will I do? I will do the updation and make this 0. Next relaxation is on edge DE. If I relax this, what happens? Distance to D is infinity, so there is no point in relaxing. E will have existing value itself, that is 6. Next, again EF, again no point because E is already infinity, so you are not going to get anything new by relaxing. I'll put infinity only here. The new weights after second round of relaxation. As of now, how many rounds are completed? Second round is done now. When I did 2 rounds of relaxation, I have this as the shortest paths to all these vertices. What does it mean when I say second round of relaxation is done? That means I have found all the possible shortest paths from source vertex to any other vertex which is containing at max 2 edges. Okay. When I do 5 round of relaxation, it will have all the possible shortest paths which are having at max 5 edges. As of now, it is at max 2 edges. Okay. So I'm going to copy these values to this particular array 0, 1, 2, 0, 6 and infinity. 2 rounds of relaxation are done. I am going to move on to the third round of relaxation. Okay. Let us see what happens in third round of relaxation. In the third round, again I'll start with the vertex AB. Initially A is 0 because it is source vertex. If I relax AB, distance to A is 0 plus 1 is 1. So this will remain as 1. Same with AC. This will remain as 2. Let me relax this edge BD now. If I relax BD, existing distance to B is 1. So 1 plus 4 will remain as 5. So distance to BD, if I relax distance to vertex D after relaxing BD will be 5. So if I see here, existing distance to D is 0. That means there is no point in doing this relaxation to give this new value 5. Existing value is 0. So why will I update 0 with 5? So I'm not going to update. Okay. Next thing is relaxation of CE. If I relax CE, what happens? Existing distance to C is 2. So 2 plus distance CE, which is 4. 2 plus 4 will be 6. This would mean distance to E that I'm finding is 6, which is already the case. So I'm not updating. I'll just write 6 itself here. Next edge is CD. This is a negative weight edge. What happens if I do that? Existing distance to C is 2 plus minus 2 would give me 0, which anyway is the existing distance to D. So I'll put 0 here. Let me relax DE now. This one. If I relax DE, what happens? Existing distance to D is 0. So 0 plus distance DE is 1. So that will be 1. New distance to E is 1 when I go through this particular edge DE. What did I do? What should I do now? Existing distance to E is 6. I will update it with 1. So I'm going to update it with 1. Next edge to relax is EF. Existing distance to E is 6. With that, if I do this F, that will be 3. So 6 plus 3 would be 9. So I have this as 9. One more edge is waiting to be relaxed, that is edge DF. What happens if I relax this edge DF? Existing distance to D is 0. So if I take 0 plus distance DF is 1. So that will be 1. New distance to F is 1. As of now I have 9. I am going to update it with 1. So 1 is the new value. After third round of relaxation. So as of now we did third round of relaxation. And what are the values? 0, 1, 2, 0, 1, 1. So I'm going to update it here. 0, 1, 2, 0, 1, 1. 3 rounds of relaxation are done. I'm going to move on to the fourth round of relaxation. Let us see what happens. In the fourth round of relaxation, again we have to go through all the edges. First, starting vertex A, distance is 0. What if I relax edge AB? When I do that, distance to A is 0 plus edge AB 1, that is equal to 1. Distance to B is anyway 1, I'll put 1 here. Edge AC, when I'm relaxing, distance to A is 0 plus weight of edge is 2. So new distance to C is 2, which is anyway the case. I'll update it here. Next edge to relax is BD. Distance to B is 1 here. 1 plus edge BD is 4, which would mean 5. Existing distance to D is 0. So there is no point in updating 5. So I'll put 0 here. Next edges, because existing distance is anyway 0. So there is no point in updating with 5. Next I'm going to relax CE. What happens? Existing distance to C is 2. So 2 plus CE is 4. That is equal to 6. But what about existing distance to E? It is 1. 1 is better. So I'll update 1 only. So basically this relaxation I didn't take into account. I updated previous value. Next is CD. When I'm relaxing CD, what happens? Existing distance to C is 2 plus CD is minus 2, which means new distance to D is 0. Existing distance is also 0. So I'm not going to change anything. I'll keep the 0 as it is. Next edge to be relaxed is this one, DE. If I relax DE, existing distance to D is 0. 0 plus DE is 1. When DE is 1, this will be totally 1. Anyway, existing distance to E is 1. So I will not update. I'll keep as it is. Next edge to be relaxed is EF. What happens if I relax? Existing distance to E is 1. 1 plus distance EF is 3. 1 plus 3 is equal to 4 is the new distance to F. But F is already reachable at a distance of 1. So I will not use this 4. I'll use the old value of 1. So 1 will be updated. Last edge to be relaxed is DF. What happens if I relax DF? When I relax DF, distance to D is 0 plus distance to F from D, DF is 1. So this will be 1. Distance to F should be 1, which is anyway 1. So I'll update as it is. I will not touch it. What happened now? I did my fourth round of relaxation. But if you see the array before this relaxation and after this relaxation, both are exactly the same. So no change happened in this round of relaxation. What did we discuss in the last lecture? In case of Bellman Ford algorithm, if there is no improvement after relaxing all edges in an iteration, you can stop the algorithm here. At max, you can go till the 5th round. But in this case, just when you reach the 4th round, you understood that is there is no point in relaxing further because there is no improvement in the shortest paths when you did one additional round. Whenever you see that there is no improvement after one additional round, that is your final answer. So this is your final answer. Distance to A, shortest path to A is 0. How is that? This is the source vertex itself. So shortest path is 0. Shortest path to B is 1. See, you can reach B in 1. Shortest path to C is 2. You can reach C in a distance of 2. Shortest path to D is 0. How is it? 2 minus 2. So you can reach D at 0 distance. Shortest path to E is 1. How can you reach E in 1 distance? You go 2 minus 2 plus 1. That is how you reached E in 1. How can you reach F in 1? You have to do 2 minus 2, then 1. So these are the shortest paths. Here, using Bellman Ford algorithm, we found shortest paths to all the vertices. Next lecture, we'll go through how to write code for Bellman Ford algorithm, and we'll also discuss about time complexity and space complexity of this algorithm. Okay.